In this video, I will explain an important chemical concept, which is the atom. The first thing I'm going to do is define several terms that we'll use throughout this video and all future videos. So the first thing to talk about is the element, or elements. They are defined as substances found on the periodic table that cannot be chemically interconverted between each other. So what this means in a practical context is if you look at your periodic table, it is chemically impossible to convert hydrogen atoms into helium or vice versa. It is impossible to take any element that you see here and produce a different element in a chemical environment. So what we mean by a chemical environment is basically a laboratory setting and all the tools that a chemist would have at their disposal in that type of laboratory setting. So you may propose, what if I just fill a balloon with a bunch of hydrogen atoms and fill it enough that the pressure is high enough that the hydrogen atoms are colliding with each other so frequently that it may be possible for two of the hydrogens to fuse together and form a helium atom. Well, this is impossible because the energy is not high enough to allow for such an event to occur. But there are instances in the universe in which there are high enough energies in which you could have that exact event. Some examples are stellar supernova and particle accelerators. In either case, those are such high energy situations that you could fuse two hydrogen atoms together and produce helium. And this concept of fusion is how all of the atoms on all of the elements on the periodic table were created initially. So the reason I go through all of that is to explain why this chemically stipulation is here in the definition of the element, and to give a little background of how the elements form. So now, the next thing to talk about is the atom. The atom is the simplest unit of a chemical element. So what this means is we can see specific atoms and distinguish them as specific elements. So we can know immediately that an atom of helium, for example, is different than an atom of hydrogen. And I'm going to illustrate how that is obvious and how we can use that to our advantage throughout our use of chemistry. Now, one thing to mention here is that atoms are not the smallest thing that we can observe. We know that things make up atoms, other particles make up atoms, but those things, the subatomic particles that make up the atom, cannot be distinguished from any specific element. So with that, we will now define what makes up the atom. So the three subatomic particles that make up the atom are protons, neutrons, and electrons. Protons and neutrons exist in something called the atomic nucleus. And again, I'm going to illustrate this in a minute. The electrons orbit around that atomic nucleus in an allowed space called the electron cloud. And again, I'm going to illustrate this in a minute. So now a little bit more information about each one of the subatomic particles. The first one to talk about here is protons. Protons have a localized positive charge. So the reason I use the localized term here is because there is such a thing as delocalization of charge. So it's very important to know the difference up front so it's not so confusing when we get into charge delocalization. So what localized means is that the charge is stuck to the proton, essentially. So if somehow you removed the proton from the atomic nucleus of any given atom, it would still have that positive charge that it started with. It couldn't be removed in any way. It's an intrinsic property of the proton itself. So delocalization means that those charges are shared between different particles, which is something that we'll show again a little bit later, but protons have this localized charge. Okay, and the next thing to notice is that they have a normalized mass to 1 atomic mass unit. So protons have an actual mass in terms of like grams, kilograms, or pounds and ounces if you want to think about it that way, but we don't use that convention because when you think about an atom, you think it's a really, really small thing. So the things that make up an atom are even smaller. So instead of using ridiculously small values for grams or kilograms of the mass of a proton, we have created a convention to talk about masses in relative terms. So it's a lot easier in this way to say that, oh, I have a 10 atomic mass unit element, so it's easy to think, oh, maybe that's 10 protons. But if the same chemist tells you that I have a mass of 10 to the negative 25 kilograms, it's much harder to think how many protons may be in that mass. So really, this convention was created out of convenience, just so we can better communicate more efficiently using this relative convention here. Okay, the next thing to talk about are neutrons. Neutrons have no localized charge, which is why their root in the word is from neutral, because they have no charge. They also have a normalized mass unit, normalized mass to 1 atomic mass unit, 1 AMU. So one thing I want to point out here is these are approximate values. The protons and neutrons do not weigh exactly the same. They are extremely close in mass. So that's why in most contexts it's okay to say that they're the same. But if you need to be extremely precise, it is important to know that they are slightly different in mass. And the last subatomic particle is the electron. Electrons have a localized negative charge. So that negative charge is equal and opposite of the positive charge of the proton. So what that means is if in any given element or atom of an element, you have the same amount of protons and electrons, the proton's positive charge is exactly canceled by the electron's negative charge. And lastly, they have an atomic mass unit of 1/1800th of an AMU. So what that means is you need 1,800 electrons to be the same mass as a proton or a neutron. So essentially, their mass becomes negligible if you're thinking practically here, because we're never going to have 1,800 electrons per 1 proton. So most of the time, the mass of the electron is ignored in most chemical contexts. Okay, so now with that, how do we put this together? So here's a general depiction of an atom. So again, like I mentioned before, we have the protons and neutrons located in the atomic nucleus, which I've circled here with the black ink. The protons are indicated by the lowercase p with a superscript plus, and the neutrons are indicated by the lowercase n with the superscript 0. So again, the plus refers to the positive charge that the protons have, and the 0 is telling you that this neutron has no charge. And lastly, you have the electrons, which have a negative charge. They're indicated by lowercase e with a superscript negative. Now notice I circled the electrons like minus to indicate the negative charge. Now I did this intentionally because some professors and some textbooks may or may not circle the charge. So you just need to be familiar with either convention. They mean exactly the same thing. So don't be thrown up by that if it's a little bit different. Now, the next thing to notice here is the protons, like I mentioned, they have a very high mass relative to the electrons. So the protons and neutrons are basically a stationary object. They're so massive that they're not going to move. The electrons are the things that are moving around the atomic nucleus because they have much less mass, so they can move around more freely. So the last thing here is we have 2 protons. So from that, we can tell exactly what atom it is. Remember that I said that the atom is the smallest unit that can distinguish what element we're talking about. So the fact that this has 2 protons in its atomic nucleus tells us exactly what the element is. And that leads me to my next point, which is the atomic number. So the atomic number is defined as the number of protons that a given element contains, and this defines that element. Okay, so the periodic table is organized in order of increasing atomic number. So 1, the hydrogen atom is element 1, that its atomic number is 1. So what that means is its nucleus, its atomic nucleus, has 1 proton. Helium, for example, now is element 2. It has atomic number of 2. It has 2 protons. in its atomic nucleus, and so on. Lithium has 3 protons, beryllium has 4, and boron has 5. This is why earlier when I mentioned let's take 2 hydrogen atoms and collide them together and get a helium, well, that kind of makes sense from a proton counting point of view. You have 1 proton in 1 hydrogen atom, the second proton in the second hydrogen atom. If you just add them up, it would be reasonable to get a helium atom. But like I mentioned with the energy situation, it is not high enough for that kind of fusion event to occur. Okay, so that explains the atomic mass. And the last thing to talk about is the mass number. This is the sum of the protons and neutrons. So this is basically the mass of the element, because we said that electrons have such small masses that they're basically negligible. So therefore the mass that that atom has is typically just the sum of the protons and the neutrons, because they're the major contributor to the total mass of that particular atom. So what this implies is if you have a mass number of 20 and you know the identity of the atom, you can then distinguish the number of protons and neutrons that that atom must have. Okay, so what all of this suggests is that if you change the number of protons, just like on paper, from one atom to a different atom, it would then no longer be that element. So if you just say I have a hydrogen atom and you want to add a proton to it, that would change the identity of that atom. It would no longer be hydrogen. But this is not true for electrons and neutrons, which is where we're going next. So the last thing to talk about here is the idea of ions and isotopes. So like I just mentioned, the proton number cannot change, and it retain the element that it is. If you have 2 protons, you know exactly what element it is, and if you make it have 3, it is now no longer that element. But if you do the same situation with electrons and add or remove an electron, then it is now still that element, but you have changed the total number of charged species in the atom, which we'll illustrate here what that kind of looks like. Then isotopes are the other version where if you change the number of neutrons, that will change the mass number, but again, the proton number cannot change. Only the neutrons or electrons can change, and it still be the same element. So now using this, we can go back to our picture here of just a generic atom, and we know that we have 2 protons. So that means it has an atomic number of 2. So without any more information, we can tell that this is a helium atom, because we can go to our periodic table. We see that helium has an atomic number of 2. That means that the atom must have 2 protons to be helium, and that's what we have here. So it is in fact, this is a depiction of a helium atom. Then the last thing to notice is it must have no total charge, no net charge, because the atomic nucleus has 2 protons, that's 2 positive charges, and 2 electrons, that's 2 negative charges. So 2 minus 2, we end up with no net charge. We end up with a 0. First type of question is just determine the number of protons, neutrons, and electrons for oxygen-16. So the first thing I want to talk about here is we have this formation, this notation here of oxygen-16 means that this 16 is the mass number. Okay, this can be illustrated many different ways. So a common convention is oxygen-16, like this, O16, the superscript on the left means the mass number. Or you could also see it like this, where it's just the element oxygen, which is O, and then 16, where this hyphen 16 again means the mass number. All of these mean mass number. So, okay, we know all of that information now, but the fact that it's an oxygen atom tells us exactly how many protons it has. We don't even have to think anymore. We just have to go to our periodic table and we look for oxygen. We see that oxygen is element 8. That is the atomic number of that element, so we know that oxygen has 8 protons. So the fact, since this is oxygen, we know it has 8 protons. So again, I'm going to use this shorthand notation with the lowercase p with the superscript plus to mean protons. Okay, now what about the neutrons? Well, we know that the mass number is the sum of the protons and the neutrons. So mass number I'm going to indicate as Mn equals protons plus neutrons. So we can use this equation if you want to figure out the number of neutrons that we have. So we know our mass number is 16, proton number is 8, and we're looking for the number of neutrons. So you basically just take your 16 minus 8, and you'll end up with 8 neutrons. Okay, and the last thing to figure out here is how many electrons we have. Well, in this question, we aren't given any information about the electrons. We just know that it's an oxygen oxygen 16, which means its mass number is 16, but we're not told anything about the electrons. And since we're not given any information there, we assume that the atom has no net charge, which means that the number of electrons must equal the number of protons. So therefore, there must be 8 electrons as well. So this example just happened to have 8 of each, but it's very common for these numbers to not be the same. And the next example will show that. Okay, our next example is a little bit more difficult. There's a lot of information to unpack here, but it's the exact same question that we just solved, but with a different atom. So again, we're looking for the number of protons, neutrons, and electrons. So the easiest thing to tell us the number of protons is the identity of the element. So we know that this is sulfur. So using our periodic table and that fact, we can easily figure out the number of protons. The next weird thing is this 2 minus superscript. What the superscript is telling us here is that we have a net charge, and the net charge is -2. Okay, so we'll have to think about how we're going to end up with a net charge of -2. And the last thing to point out is the mass number. Now, the mass number in this case is 33, and if we recall, that is the sum of the neutrons and the protons. So, using our periodic table, we find sulfur. That is atom 16, element 16. So that means that we have 16 protons. The fact that this is sulfur, there must be 16 protons. Now, using the the mass number, we can then figure out the number of neutrons. So we know that the mass number is 33, and then we have 16 protons. So that means we have 17 neutrons. This uses the same equation in the previous example that we used here, where the mass number equals protons plus neutrons. That's what we used here. We plugged it in to find the number of neutrons. Now, the most confusing part of this question is how do we end up with a net charge of -2? Well, we know that the protons and the electrons are the only charged things in our charged particles in our atom. So in order to have a net charge of -2, we have to have 2 more electrons than we do protons. So what that means is if we have 16 protons, then we have to have 18 electrons in order to satisfy the condition that we just said. If we need a net charge of -2, we need to have 2 extra electrons than protons. Many students might get confused here and suggest, well, why can't I just have 14 protons and 16 electrons? And that would still give you a net charge of -2, but the reason that's wrong is because if you have 14 electrons, you no longer have sulfur. Remember that the number of protons defines the identity of the element, so manipulating the protons will also change the element. That's something we can't do in this type of situation. Okay, now the last example is talking about isotopes. Remember, isotopes have they're the same element, but they have a different number of neutrons. So this will change the mass number and no identity of the element will change. So this question is asking which of the following are isotopes of carbon-12. So again, here's another notation. Carbon is the atom, is the element that we're talking about. 12 is the mass number. So we're looking for something that is also carbon, but with a different mass number. So Boron 12, we can immediately throw that out. That's not a isotope because it is a different element. It has a different number of protons. It's no longer carbon, so it can't be an isotope. An isotope must be the same element but have a different number of neutrons. So using that same logic, it cannot be nitrogen 12 either. It is carbon 13 because remember, here's another notation saying that it's a mass number of 13. So that means that there's one extra neutron in that atom compared to carbon 12. And same logic for carbon 14. This is also an isotope. This one now has 2 extra neutrons compared to carbon 12. All right, with that, that'll do it for this video. I hope you learned something. If you did, please leave a like. And if you're new to the channel, please subscribe. Otherwise, I hope to see you in the next video, and happy studying.